just learned that slope is needed for developing a formula, creating a formula that governs a physical system. Apart from slope, something else is needed to make that formula or equation that governs a physical system applicable and correct. What is that? It is called intercept. Intercept is the second factor. A second factor obtained through straight line graphs, which we need to be able to create equations that help us predict the character of a particular physical system. So I ask, what is intercept and how does it cooperate with slope towards creating a formula or equation that controls the character of a physical system? That takes us to lesson number 6, and that is the meaning and application of the intercept. Please join me as I develop this section.
Let us use the same Cartesian plot, same Cartesian sketch to explain the concept of intercept. What is intercept? Intercept is the value of a variable at which it begins to vary with another variable. What do I mean by this? This definition may not be sufficient for us to get the exact meaning of this concept called intercept. Let me explain with this Cartesian plot. But first, recall that this table is what gave us the values with which we got this Cartesian plot or sketch here. X may not have real life meaning. Y may not have real life meaning. But for us to understand the meaning, or for us to get the meaning of intercept, let me give X and Y real life meanings. Please watch the following diagram. This diagram illustrates the extension of a spring when a mass is hanging onto it. This is a spring. This is a mass hanging onto it. We know that in real life, when a mass is hanging vertically downwards this way on the string, that the consequence is that the spring may extend downwards. While M stands for the mass of the object hanging on the spring, let E stand for the extension, that is increase in length. Please, think about it. If this mass is in kilograms and this extension is in millimeters, what it means is that every unit kilogram of mass will produce a particular unit, a particular amount of extension in millimeters. Right now, just think about it again. What if I bring a piece of paper and hang it onto this spring? Paper has mass. We know that the mass of paper is not zero, but the extension will not be produced, meaning that the mass of that paper will be insufficient to produce any extension on the spring. Therefore, mass has started increasing from zero to something more than zero, but the extension has not even begun to show. I can even put up to 2 grams of object onto this spring, and this extension is still not showing, depending on the stiffness of this spring. If the spring is so stiff, it might take several kilometers to produce an observable extension in millimeters. But one thing is very clear now. It is not the very time you start putting the mass that the extension starts being noticeable. Now, the value of this mass at which it begins to produce extension is what we refer to as intercept. The intercept for the mass, which means a particular value of the mass which it attains before it begins to vary with extension. Notice that, or recall that the moment appreciable mass hangs on this spring and it begins to extend, from that time onwards, you will now notice that each time there is any mass added to the former mass, you're going to see more extension. From that time, any increase in mass will produce an increase in extension. Already, the mass changing will produce a change in extension. That was not the case from the start. It is only when mass has crossed a value or reached a particular value that the extension began to increase. But once this begins to happen, then extension and mass begin to relate with each other. At this point in time, they begin to vary with each other. That limit of value of mass at which it begins to vary with this extension is an example of intercept. Recall that I said that intercept is a value of a variable at which it begins to vary with another variable. Now watch this statement. It says, if extension begins to occur only after mass has reached 3 kg, then intercept for mass is equal to 3. I hope the statement is clear. In this case, the mass did not produce extension in the beginning until it became 3 kg. It was only after it reached 3 kg that it began to produce noticeable extension on the spring. Because of that, mass and extension, even though they began to vary afterwards, did not begin to vary at the same time. They began to vary only after the mass had reached 3 kg. With this statement, we can also define intercept as a value with which a variable leads or lags before it begins to vary with another variable. Now, let's turn our attention to the Cartesian sketch, which we have just done before. Don't forget that this sketch came from this table. Assuming that this is a table summarizing what happened in this spring. That is, this x is the mass and y is the extension. We know that without mass, there will be no extension. Likewise, without x, there will be no y. What it means is that this x is now written to represent this mass. This is real life. This is purely mathematical. This is real life. This is purely mathematical. But in every case, we should recall, or we should bear it in mind, that each time we solve a mathematical problem, that is a real life problem, it could have solved somewhere. That is the beauty of mathematics. Let's make progress, please. If x is the mass in kilograms and y is the extension in millimeters, what it means is that when 1 kg was hanging on this spring, 7 millimeters, we had extension. When 2 kilograms were hanging, the extension was 9 millimeters, and so on and so forth. This is therefore the summary of an experiment carried out with this spring. And this is the Cartesian sketch for the table. Now, how do we know from this sketch the intercepts? Meaning, between x and y, which one is leading and which one is lagging? You observe that from here, the y which is the extension, leads. Even though in real life it can't lead, but here, if y is for this extension, and then x is for the mass, let's assume that the x is for the extension and y is the mass, because it is not out of place to sketch the plane the other way around. That is to say, placing what is independent here and placing what is dependent here. In fact, that is what is playing out at this point in time. The reason is that we can't possibly expect the extension to lead. So what must be here must be the mass. If mass is what we expect to be here, what it means is that the mass leads and then the extension lags. From that sketch, how do we get the intercepts? Before then, don't forget the meaning of extension. Don't forget the meaning of intercept. The value with which a variable lags or leads before it begins to vary with another variable. Mass leads over extension before it begins to vary with extension. Therefore, what value is it that the mass leads with? That is the intercept for the mass. And what value is it that the extension lags with? That is the intercept for the extension. What it means is that both variables are expected to have their own intercepts. Now, obviously, after we make Cartesian sketch like this one, it is where the line of best fit crosses the axis. The value of the variable where the line of best fit crosses a corresponding axis is where we call the intercept for that particular variable. Take, for instance, this y and this x have positions where this line of best fit crossed them. Look at where it crossed the y. The value of y where this line of best fit crosses it is 5. Therefore, the intercept for the y is 5. What about the x? But first, is this 5 a lag or a lead? That is, has this y increased out to 5 before it began to vary with x? Or was it below or lagging by 5 before it began to vary with this x? Obviously, from this 0 to 5 is positive, which means positive is lead, and then obviously negative is lag. Because of this, y leads by 5. Then we expect that x is going to lag by a value. What then is the value with which the x is lagging? It corresponds to this point here. Let's try and estimate the value with which x lags before it begins to vary with the y. If we take our time to calibrate the left-hand side of the x-axis, we see that we have -1, -2, then you go here to have -3. Then where then is this intercept? By estimation, it is approximately equal to -2.4. Therefore, the x-intercept is -2.4, while the y-intercept is equal to 5. What this statement means is that before the x and y began to vary, that is, began to change accordingly with each other, y was leading by 5 units and x was lagging, that is, behind by -2.4 units. That is the implication. Therefore, the y-intercept is 5 and x-intercept is minus 2.4 approximately. Now again, we turn our attention to the intercept. Don't forget that intercept is defined as the value with which a variable leads or lags before it begins to vary with another variable. Let us use this second example of Cartesian plot to look again at the concept of intercept. And afterwards, we intend to compare the results we're going to get here with what we got earlier, especially with strong interest in consistency. Now, watch this sketch again. What are you seeing? But before you tell me what you are seeing, do you remember how to get the intercept? For the second time, let me say it. The intercept corresponds to the positions on the axis where the line of best fit cuts across them. This position is an intercept. This is also an intercept. This is x-intercept, while this corresponds to y-intercept. Therefore, once we get the value of x here and the value of y here, we've just got the values of the intercepts. Let us see how to go about it. Already, if you watch this place, you realize that there is nothing that is marking, there is no value marking this position. This 1 marks this position, but nothing is written here to mark this position. But this is where the line of best fit crosses this x-axis. It is now our duty to get the value of x at this point. What is the value of x at this point? We're going to do it by approximation. The same thing is applicable to this y-axis. What exactly is the value of y at this point? This minus 4 marks this point, but nothing is written to mark this point. But still, this y-axis has a value at this point. Again, it is our duty to find out the value of this value corresponding to the y-axis. What do you think, please? From here to here and here to here are roughly equal. Don't forget that this is a freehand sketch on a Cartesian space. Likewise, we can approximate the value of x at this point. If we have an instrument of precision, we would use it to find out the exact value of x at this point. But because we don't have it, since we have a freehand sketch, we're also going to get the value of this x by approximation. If from here to here and here to here are nearly equal, and from here to here is 1, what it means is that from here to here is half of 1. As a result, the intercept on x is half of 1. How do we write half of 1? It is 1/2 or 0.5. That takes us to stating that the x-intercept, otherwise known as horizontal intercept, is equal to 0.5, approximately equal to 0.5. See it here. Look at the way it is here stated. Now, what about the axis, the y-axis, the vertical axis? Its intercept corresponds to this. In like manner, let us see the value of y at this point. Again, if you watch from here to here and imagine its distance, you will also see that this point where the line of best fit cuts the y-axis is like half of this distance. If from here to here is 4, and from here to here is half, what it means is that from here to here is half of this 4. What is half of 4? It is 2. Therefore, this intercept is 2, not just 2, minus 2. Why? Because anything going from this origin vertically downwards is going the negative direction. Watch that this is minus 4 and this is minus 8. It means that this negative y is calibrated with negative numbers. Therefore, what we're going to see written here is not just 2, but to indicate its direction, we're going to see minus 2. Let us see. Again, like before, see it that corresponding to this position is a value of intercept, which is approximately equal to minus 2. In fact, even if we have instruments of precision, certainly this minus 2 will still be the intercept for the y-axis or vertical vertical axis. That is why we state that vertical intercept, whose symbol is C, don't forget, is equal to minus 2. So far, we have had 2 examples of intercept, how to find intercept, having known its definition. I believe that in real life, we now know what intercept does for us. Anyway, we see more of it when we look at intercept again with respect to using it to derive equation from a Cartesian sketch. Checkpoint. It says, show each of the following tables on a Cartesian space, and therefrom obtain the slope and intercept where possible. It is believed that this instruction is clear. Find the slope and find the intercept only where doing such is possible.